Okay, so last time we were talking about chapter 1, and in there is basically we're just doing some basic techniques of integration just to remind ourselves what an integral is, how to calculate integrals, and so on. Now, there are still more complicated integrals that we have not discussed how to deal with. But before we do that, let's stop a little bit and let's look at some applications. In particular, we're going to see how we can use integrals to calculate area, which is actually, when they were defined for this, to find area. But then we're also going to take advantage of this idea to calculate volumes. So that's what I'm going to do now in this chapter 2. And then we're going to come back to chapter 3 to learn more advanced quotation mark techniques in solving integrals. Okay. All right. So as a plan, so let's go ahead and let's begin. I'm going to give you the general idea to establish some formulas, and then we're going to do examples. Okay. Here, your knowledge from pre-calculus will be needed, because one thing that will be important is that to do these problems, you need to sketch the functions. Okay. Because when you're finding area, you need to know what curve is on top and what curve is in the bottom to be able to correctly set up your integral and calculate. If you don't draw a picture, it's not that straightforward to see. Okay, so here you will have to be able to sketch. Also, when we talk about volumes, you will need to sketch you don't have to sketch the three-dimensional object, but you will need to sketch the region that will be rotated. You will see what that means when we discuss it. Okay, so in other words, graphing curves is important. So if you don't remember this too well, you need to go back to, let's say, college algebra, and there you had a list of basic functions, how they look like and so on, and transformations. You should take a look at that. Okay. All right. Anyways, you will see in the examples now, but let me set up the idea. So to begin, let's suppose that we have two functions. So let f and g, let f of x and g of x be two curves. And then let's say that they are continuous. They are continuous on the closed interval AB. And moreover, let's suppose that f of x is always greater than or equal than g of x on this interval. Okay, so I'm just gonna draw an arbitrary picture here. So let's say here is A, here is B, and then we have the function f over here, and then the function g is somewhere below the function f. It doesn't really need to be both them above the x-axis. They could be below the x-axis or g below the x-axis. It doesn't matter. What I care about is the fact that g is greater than f is greater than g over the interval AB. Okay. The question that we are interested in is the following. So we look at the line x equal a and x equal b. So those vertical lines. Then this defines a region. The region bounded by the two functions, bounded above by f, bounded below by g, and to the left by x equal a, and to the right by x equal b. And the question that we are asking is, we want to find the area. So find the area between f and g. Okay, this is what we want to figure out. So given a situation like this, how do we calculate the area between the two functions? And the idea is actually pretty similar. You can use the old idea, which is the fact that the integral from a to b of, let's say, of the function f is the area under the curve. So that would be this whole piece right here, including the white part. And then you subtract from it the integral of g, and you're going to end up with the shaded part. But instead of doing it that way, let's go ahead and let's calculate the area directly, because this mindset is what you need when we start talking about volume. So it's good to do this from the beginning. So how do we solve a problem like this? So we have our interval AB. So the idea is that we're going to split the interval into little pieces, because we want to fill this region with a bunch of rectangles, and we want to approximate the area with rectangles. Okay. So we just split this into a bunch of pieces, all of which are the same distance. We call that distance delta x. Let's say this is this is the ith interval. Suppose this is xi plus 1. I is just an index, okay, that runs from 0 all the way up to n, and split this into n pieces. And then this right here, delta x, which is this little interval, is going to be the base of my rectangle. So I'm going to go here and then pick a point inside that interval. Let's call it Ci. And the value of the function f at ci, I'm going to evaluate that. And then the value of the function g at ci, I'm going to evaluate that. That's a point down here, and that's going to be the height of my rectangle. Okay, so I'm going to have a rectangle here. That's going to have height. The top of the rectangle is the value of the function at ci, the function f at ci. The bottom of the rectangle is the value of g at ci. Okay, and the width of the rectangle is delta x, which is this tiny little piece, the partition that we did of the interval AB. This is always taken to be b minus a over n. Okay, because we're splitting this into n pieces, all of which are the same. So the idea is that we have a bunch of rectangles. I just draw here one rectangle, but for each little interval that we have, we're going to have a little rectangle with this property. Okay, so let's call this the ith rectangle. So this is the ith rectangle. And then what's the area? So ARI, this is the area of the ith rectangle. How do we find the area of a rectangle? So the area of a rectangle is base times height. So this time the base is delta x and the height. Who can tell me how we can calculate the height of this rectangle? So that would be the top value of the function at ci, right? If we're only looking at this little rectangle, right? The top value, so top minus the bottom. Everybody understand this? That's the height. So that would be f of ci minus g of ci. Ci is an arbitrary point inside. Let me write it here. Ci is between xi and xi plus 1. It's just whatever point you want inside that interval. Okay, it doesn't matter because at the end, remember, we're going to take a limit as n approaches infinity. So this interval, the length of the interval is going to approach 0. B and A are constant. So when you take the limit, B over A minus n is 0. So the interval becomes very tiny, and all these points in here, they become 1 point in the limit. So it doesn't really matter which one you pick. So that's the height, and then times the base. Okay, so the area that we are interested in, let's call this area A, the area of the region between F and G, can be approximated by adding the areas of all of those rectangles. There are n rectangles, so the sum from 1 to n of the area of the ith rectangles. So that is sum from 1 to n of f of ci minus g of ci, and then all of this multiplied by delta x. That's an approximation, and then as you know, how do we define the area? If you want to get the exact area, we want to take as many rectangles as possible, so we take the limit. Okay? So A equals the limit as n approaches infinity, so we want to take infinitely many rectangles of this sum. And if you remember from our discussion last time, this is precisely the definition of an integral, right? We can write this sum, this is a Riemann sum, and we can write this using an integral. Who can tell me what is this integral?
The integral bounded between a and b, and then that would be f of x.
F of x.
Minus g of x.
Minus g of x. That's our function. This is the function that we are integrating. F of x, f minus g. Okay. As a whole. And then the delta x becomes dx. Right. So this is the formula for the area. The bottom line here is that when you have two functions, and if you want to calculate the area between them, then all you have to do is figure out what's the top curve, what's the bottom curve, and then is the integral from a to b of top minus the bottom. It's very important to know who is on top, because if you switch this, then you're going to have minus in front. You understand this? So you're going to get the wrong answer. Yes?
So if you switch them, like let's say you put g of x accidentally in front because you don't graph it, would it automatically make it a negative? Or
you're going to get the negative version, because if you switch it, this function is less than this one. So this is a negative number.
Oh, Also, it'll always be negative.
Yeah, so you're gonna get a negative value. At that point, you will realize that something is wrong because if you calculate area, you're looking for something positive. This is something else. If you have a problem that tells you find the area of or find the volume of, and you're doing your problem and you get a negative number, something is fishy here. Volume is not negative, area is not negative. Do you understand this? So if you get a negative number, that means, oh, you choose the wrong position, then you need to back up and switch. Okay? But to avoid that, just graph. But if it looks too complicated to graph, you can take a guess, right? And if it doesn't work, then switch it. You could do that. But then you need to work twice. That's, yes?
Couldn't you find, like, pick a number in between A and B and plug it into both and see which one's higher and lower?
You will see in the example, sometimes the functions cross. You see, you may have a problem in which the functions do this. We're going to see an example of that's happened. Let's say you have a polynomial, right? And I don't know, let's say parabola. Let me see, is that happening here, what I want? Let me do this. And let's say that you want to find the area bounded by the two curves, the red and the blue, right? So you need to do bounded by the two curves. So I'm talking about this piece together with this piece, right? That's what you need to find. Now, in the first piece, in the yellow piece, the red is on top and the blue is in the bottom, right? That's one integral. So from whatever this point of intersection is to this one over here. And then the plus, there's another integral. You need to add the two integrals, right? Because you add the two areas. And then you need to switch them because now in the next interval, the blue is on top and the red is in the bottom.
Can you just do it whichever way and get rid of the negative symbol because you know area is not negative?
But like I said, this one, for example, this problem requires two integrals to solve. You cannot do it in one integral. If you don't graph, then I'm gonna see this. You can do it without graphing, but then you need to do heavy algebra. It's easier to just graph. Okay? And you will need to find these points of intersection to know what they are because you need to know your limits of integration, right? Typically, you're not gonna be told the limits of integration. You need to find them. How? You graph. You will see, we're gonna do in the examples. So be careful because, you know, if I tell you, let's say from A to B, which is the left endpoint and the right endpoint, if you pick a point here, then you will get that the red is bigger than the blue. But if you pick it here, it's the other way around, right? So. All right. But if you know that the functions do not cross, then yes, you can do that. But you need to know if the function cross or not. Okay, so anyways, the moral of the story is, so theorem, the area between the two functions can be calculated by the integral from A to B of f of x minus g of x. Okay? Dx. And what you should take from here is, because of this, remember that difference of the functions is really define the height of the rectangle. So in this case, it's always top minus bottom. So as the integral from A to B of whatever the top curve is minus the bottom curve. Okay? Now, sometimes, and this is always when you integrate with respect of x, okay? So if you integrate with respect of x, you will always be doing top minus bottom. But sometimes you may want to integrate with respect of y because it's easier. We're going to see an example in which it's easier to integrate with respect of y. Because sometimes with respect of x, you will need to split into two integrals, but with respect of y, you can do it with just one integral. But when you do that, instead of partitioning, placing your rectangles vertically, you need to place them horizontally because you have to partition the y-axis instead of the x-axis. And you're going to be moving the rectangle like this. You're going to fill the area with rectangles that are horizontal. So in that case, your differential will be dy instead of dx, but there is no top and bottom, right? So what you want is the width of your rectangle will be delta y, but then the length of your rectangle in that case will be right minus left function. Remember, vertical rectangle is top minus bottom because that's the height. But when the rectangle is horizontal, you want to do right minus left. Okay?
Positive.
Well, this could be happening on the negative part. But just think about if you have a rectangle like this.
Yeah, but the most positive it would be the top.
Yeah, exactly. So how do you find this length?
Take
whatever this is. Let's say this is D and this is C. So how do you find that length? You do D minus C. You don't do C minus D, right? You do D minus C. So it's right minus left. Now this will be defined by some function, and this will be defined by some function, so you subtract. Okay? And similar to this, but instead of top minus bottom, right minus left. And we get to an example, then I will do it. So let me just say here, similarly, if the region is bounded by two curves that are defined in terms of y instead of in terms of x. So for example, x equals f of y, and x equals g of y. So think of, let me just give you some sort of picture. Let's say here you have your f of y, and here you have your g of y. Now this time here is c, here is d. You want to find this area. If that's the case, again, just think about the little rectangles. You know, you just split this into equal pieces, etc. So just pick a rectangle here. This is our delta y, and then the area of the rectangle. The area of the rectangle this time is going to be the right curve evaluated at some point. Let's call it, I don't know, I use C, so let me use M. So f of mi minus g of mi. What is this mi? Mi is just a point here. Okay? And then times the thickness of the rectangle, which this time is delta y, which is, you know, the length of that little interval. Delta y here will be d minus c over n. Okay? And then similar way, we approximate by adding the area of the rectangles, we take the limit, and then we end up with the fact that the area will be the integral from c to d of f of y minus g of y. But this time, because we are moving horizontally up and down, we are moving in the y direction, we are integrating with respect of y. So the variable of integration is y. So that's why you see the dy. So just like before, to write the general form, that would be the right curve minus left curve. Okay? dy. So the dy stands for the thickness or the width of the rectangle, and then the expression in the parentheses is the length of the rectangle in this case. Okay?
Professor.
Yes.
What does dy mean?
So dy is the infinitesimal version of this delta y. So remember, when we talk about integral, this is a package. You have the integral sign together with this. They come together. If you don't write a dy, it doesn't make sense. This doesn't make sense. If you don't write this, then it's something else. It makes sense, but it's something else. It's called a differential. But just think of it as a package. You don't have to worry about that. This dy is actually what this delta y becomes to. It's something very tiny. Because remember, we're taking the limit as n approaches infinity. So this goes to 0. This becomes super small. That's what this dy stands for. Are we okay with this? All right. So I just wanted to get the formulas out of the way. So now let's do examples to see how we can apply this. Yes?
One quick question. Is there any specific reason for whenever you use y, the integrals will go from like c to d and then the x is a and b? Is there any specific reason on that?
No, I'm just using different letters. Typically, we use A and B, you know, in the x direction, and C and D in the y direction. But it doesn't matter. You can use your favorite letters. Yeah. Okay. All right. So let's go. Let's do some examples then. Okay. Are there any questions? Let's see on Blackboard. Are you guys okay? All right. Good. So let's do examples now. Right. Now we have the formulas out of the way. Let's let the fun begin. So find the area of the region R. And what I'm going to do is I'm going to describe the region in each of the little exercises that we will do. Okay. Okay. So R is the region bounded. So it's bounded by the function f of x equals x over 2 plus 5. The function g, which is x plus 1/2. This is going to happen over the interval from 1 to 5. Okay. All right. So let's see. Let's do this to get an example, to have something concrete to talk about. So the first thing that I'm going to do is, whenever you see a problem like this, the first thing that you should do is draw the region. Okay. Forget about everything else. I just sketch the region. In this case, both of the functions f and g, they are lines, right? The first one is a line with slope 1/2 and y-intercept 5. So let's sketch that. So we need to sketch both graphs on the same coordinate system, the same x and y. Okay, so the y-intercept is 5. 1, 2, 3, 4, 5. So it's gonna go through here, and then the slope is 1/2, so it's gonna go up. So you can do 1 up and 2 to the right. 6. Remember, to draw a line, all you need are 2 points. Okay, those are my 2 points. So this is 5 and this one is 6, and that's all we need to sketch our line. All right, so this is the function f. Any questions? So that's my function f. Now let's go ahead and let's draw the function g. So once again, the function g is increasing, and the slope is 1, and the y-intercept is 1/2. So that means it's gonna go through this point right here, and the slope is 1. Okay, so instead of doing that, let's find the x-intercept. So what's the x-intercept? If we set this equal to 0, x is gonna be -1/2, right? So it's gonna go to y equals -1/2. So if this is -1, then here we have. So this point here is 1/2, and this one is -1/2. Remember, what I'm doing is finding 2 points, as said. Because I know this is a line, so all we need are 2 points. This is my function g, okay? And now we want this to be from 1 to 5. So let's see. X equals 1. So that will be this region all the way up to 5. 3, 4, and 5. And let me see. Okay. So we're talking about this piece right here. That's the region that we are interested in, that we need to calculate. Do you understand this? Understand the picture? Just draw 2 lines. That's all. All right. So let's see. So we need to find the area. Now here from the picture, it's pretty clear which one is the top, which one is the bottom. So we can easily do it now. So this is A. So let's set up the integral. Who can tell me? How do I write the integral? What are the limits of integration? From where to where? So from 1 to 5. And then what do I write?
You write the f(x), which is x over 2.
So let's put the formula first. So this time the top is f, right? Minus g of x, which is the bottom, dx. Notice that this time, you know, it's very easy to just place a rectangle like this, right? Vertical instead of horizontal. Because if you place it horizontal, it's actually pretty difficult. Not difficult, but you have to split the integral into 2 pieces. Because from this point, where the region begins in the blue line, all the way up to this point right here. So you see what I mean? Up to here. Oops, it's not what I want. It's my daughter, she likes sparkle stuff. But all the way up to here, you have to split it into 2 pieces. That first triangle, okay, So you can do it with a rectangle because this time the blue is the one that is to the right, and then the line x equal 1 is to the left. But then the moment that you pass this line, your rectangle is different. Your right part is the line x equals 5. Actually, up to here, you have a little rectangle here. And then you have the other case in which the left is the red. What I'm trying to say is, if you try to do it with respect of y, it's going to be very difficult. You have to do a bunch of integrals, like 3 integrals you will need to do, okay? But if you do it like this, then you can just do it in one shot, because you always have the red on top and the blue in the bottom, okay? So when you're given a problem, you need to decide what's better for me, integrate with respect of x or integrate with respect of y. What that means is, do you want to place your rectangle vertically, like what we did now, or horizontal? Okay? You will see an example in which it's better to place it horizontal. Okay? So by better, we mean we get only one integral. Anyways, we're gonna see that in the examples. Now let's go ahead and let's calculate. So the function f is x over 2 plus 5, and minus the function g is x plus a half, and we integrate it. Okay, so combine like terms, and then we do what we need to do. All right, so integral from 1 to 5. When I distribute the negative, I get negative x. So 1/2 x minus x is negative a half x. And then 5 minus a half. So that's going to be, this is 10 over 2. So that's 9 over 2, right? dx. And now it's a polynomial. So remember, fundamental theorem of calculus, we just need to find an antiderivative and then evaluate at the endpoints. So that'll be negative 1/2 times x squared over 2 plus 9 over 2x. And then we plug in from 1 to 5 and we evaluate this. So negative 1 over 4 times 5 squared, that's 25, plus 9 over 2 times 5. That's what we get when we plug in 5, and then minus, when we plug in 1, we get negative 1 over 4 plus 9 over 2, right? And then calculate. So what is this? So negative 25 over 4. Okay, I'm just gonna plus 45 over 2, then plus a quarter minus 9 over 2. Okay, so I can easily combine these two guys. Negative 25 plus 1, that's negative 24 over 4. But negative 24 over 4 is negative 6. So that's negative 6 plus, and then 45 over 2 minus 9 over 2. I can easily combine those two. So 45 minus 9, what is that? That's 36, right? 45 minus 9, that's 36. Mm-hmm. Yes, and then over 2, so 36 over 2 is 18. So we get 12. All right, questions?
So you combine them from the beginning, right? And there's
but here just distribute the negative, combine like terms.
Would you be able to integrate one of them and then the other one and then subtract? Is that allowed?
Yeah, of course you can do that, but then you have to do two integrals.
Yeah, no, I got you.
You would do two integrals. No, at the end of the day, I mean, you will need to integrate two lines. Here, integrate one line, right? It just looks painful because you have two terms, and you plug in the limits, you actually get 4 terms. But other than that is, I mean, really the important part here is, at this point, is this, right? Being able to set up the correct integral. Then after that is just calculation, making sure that you get the correct number. Are we okay with this? All right. Any questions? No? All right, no questions on Blackboard. So let's move on. Let's see, part B. How about, so let's say R is bounded above by f of x equals x, and below by g of x equals x to the 4. And this time, I'm not gonna tell you, oh, wait. I usually put my entire screen, but now you guys are seeing, I'm gonna switch it, or is it too small for you, or you feel okay like that? Because normally I project the screen, that's not what I'm doing. You're watching what everybody's watching on Blackboard. Is that okay? Okay, I just realized that. But at least you can see what the students write. And so, okay, but let me know if you want it bigger, and then I just switch it quickly. Okay. All right, so let's do this. So bounded above by these two functions. So the first function is a line, right? The line y equal x, and this one is x equal 4. So that's a power function, and it just looks like a parabola. Okay, for all practical purposes, it's gonna look like a parabola. Just remember, it's x to the 4. So let's draw a picture. Actually, let me bring it to this side a little bit more. So we have the line y equal x. Call it f. Okay, and then we have the function g is x to the 4, so it's gonna look like a parabola. Actually, we do know where they cross. That's another point. Okay, so I know where they're gonna cross, but let's do it now. So every time that you have two functions like this, you need to figure out whether they're gonna cross or not, because if they do, you need to show it in the graph. How do you check whether two functions cross or not? You just have to set them equal to each other and you solve the equation. Okay, so let's figure out when x equals x to the 4. You should be able to guess from the picture and from the solution when this happens, right? So it's happening it's gonna happen at 2 points, right? At 0, and where else? And 1, right? But let's let algebra tell us what's going on. So this is a degree 4 polynomial. So let's solve it with factor, right? And now this is a difference of cubes. So we're gonna get x, and then this is x minus 1, and then that's x squared plus x plus 1. Okay? I use the formula for difference of cubes. Do you remember the formula to factor difference of cubes? So let me put this down a little bit. Like I said, we're gonna need stuff from pre-calc, okay? So recall a cubed minus b cubed. This is a minus b times a squared plus ab plus b squared. Okay? If you don't remember the formula, you learn how to find zeros of polynomials in pre-calculus. You just need to know, if you know 1 0, then you divide, you do synthetic division, and then you can factor the polynomial. Here it's clear that 1 is a 0, right? So you do synthetic division with 1, and then you will be able to figure out this or the factor. You know x minus 1 is 1 factor, and then you can get this by division, by dividing. Okay? Do you remember what I'm saying? You did this in pre-calculus, like finding zeros of polynomials and so on. But in this case, we can factor. And notice that this third factor here is a quadratic polynomial that is irreducible. This is prime. You cannot factor this. Okay? So this doesn't have real zeros. So this polynomial of degree 4, x to the 4 minus x, has 4 zeros. They are x equals 0, x equals 1, and the other two are complex coming from here. But we don't care about the complex guys. We only care about the real guys because those are the ones that show up in the picture. Okay? So we are only looking for real solutions here. So this one has complex solutions. So we don't worry about that. And so we get x equals 0, x equals 1. So this time I'm going to say that 1 is this. So that's going to be one point of intersection, and here is another point of intersection, and now we sketch. Okay? Let's see if I can exaggerate this a little bit more. All right, this is our function g. And then, you know, we are interested in this right here. That's a region bounded by the function f and the function g. this little piece right here. Do you understand this? So it turns out by looking at this, we can see that f is above and g is below. Okay? So here, actually, you could place rectangles however you want. In this case, you know, since the functions are already given to us in terms of x, then it's easier to integrate with respect to x. So I'm gonna place my rectangle like this. Okay? But you may want to place them also horizontally, and then you integrate with respect of y from 0 to 1. That also works. Okay? But there's no need to do that here. All right, so let's find the area. So the area is gonna be the integral from where to where? From 0 to 1. And then which one goes on top? So f goes on top, and g goes in the bottom, right? And once again, we are integrating with respect of x. All right, so let's see, what's our function f? That's just x. And what's the function g? That's x to the 4. Dx, and then we do this using power rule, right? So 1/2 x squared minus 1/5 x to the 5 from 0 to 1. And basically this is 1/2 minus 1/5 minus 0 minus 0. And 1/2 minus 1/5. So you can quickly multiply here top and bottom by 5, and here multiply top and bottom by 2. So we get 5 minus 2, that's 3 over 10. All right, questions? Are you okay with this? All right. So let's bring some trig into the mix. We haven't done much stuff with trig yet. So let's do some. How about C? And then R is the region between f of x equals sine of x and g of x equals cosine of x. And let's do this over pi over 2 to 2 pi. So as quadrant 2, 3, and 4. Okay. All right. So again, the first task is to actually sketch these functions. So let's do that. So let's graph these functions and then let's figure out the region. So that's x and y. So let's say this is 2 pi over here. So I'm going to split this into 4 equal pieces. That's pi over 2. That's first quadrant. Then pi, that's quadrant 2. 3 pi over 2, that's quadrant 3. And then 2 pi, that's quadrant 4. Let's sketch sine. That's the sine function, as you know. The sine function is a sinusoidal function, and it goes between 1 and -1, right? So let's say 1 is here, -1 is here. So it starts here on top. No, it starts at 0, then go up here to the top, down to the middle, then down here, then back to the middle, and then sketch the graph. That's the sine function, and then it continues, but we don't care about what happens after. I mean, it's the same thing over and over, to the left and to the right. So that's the function g. This is the function f. And then for the function g, that's the function cosine. It's very similar. It's just that it begins at 1. So it begins up here, then it's down here at 0, then down, middle, up. And it has this shape. That's the function g of x. Okay, All right, so we are interested in the integral from pi over 2 all the way up to 2 pi. So that means that we are interested in this region. I mean, the area from pi over 2 to 2 pi. So we are interested in this region together with this other region. So the reason why am I changing colors? Why is it two different intervals?
Different intersection.
Because one function is above the other on one
Because the
side.
position of the functions are switching, right? Remember, the fact that, I mean, they could be like this, you know, you could have a function like this and then something to this, and they could, you know, cross right here, but what, touch there, but if the red is always on top and the blue is always in the bottom, you can just do one interval. There's no need to do two intervals, okay? It's just because the red and blue, they are switching position, right? From between pi over 2 and 2 pi.
Aren't they equal to each other? So can you just do one and multiply?
How do you know that they are equal to each other?
Because it's sine and cos, because they're like exactly the same.
You have to convince yourself that that's the case. But for that, you need to figure out, we first need to know what this point is. You don't know what this point is yet, right? We need to find out what is this point. So, but yes, you may be right, but you need to argue. You know, you need to argue that why, I mean, you're claiming that this shape is symmetric to this one. In other words, if I were to draw a line here, a vertical line like this, you're claiming that this line will be like a mirror. That the blue shape reflects exactly over the yellow shape. That's a strong claim. So then you have to somehow just back it up, right? So instead of doing that, just gonna compute the integrals. Okay, I think it would be more. It's easier. Okay, so do you understand that we need to find this point? Because we need to know where the first integral stops, and that's exactly where the second integral begins, right? So that point is important. So we need to find this point, the point of intersection of the two functions. And in what quadrant is that point? By looking at the picture? Are you sure?
It's the first one.
Is it the intersecting point? Yeah, the x value of this
Oh,
point.
the point you're talking about.
So remember, we're looking for this point. When I say I want to find the point, well, I mean the x. I don't care about the y, right? We're just working with x's here.
It
So
would be between 1 and 2.
where is this point? It's bigger than pi, less than 3 pi over 2. So what quadrant is that? That's quadrant 3. Remember, when you think about angles, yes, this is quadrant 1, 2, 3, 4. But when it comes to functions, when you graph the trigonometric function, it's different. This little interval here from 0 to pi over 2 represents quadrant 1, right? This represents quadrant 2, quadrant 3, quadrant 4. Just think about the ranges, right? So 0, pi over 2, pi, 3 pi over 2, back to 2 pi. This is quadrant 1, which turns, this comes from this interval right here, right? Between 0 and pi over 2. It's just that here we're looking at angles on the right, while on the left we're looking at the functions, two different things, right? On the left you have the y values, here we're looking at the angles themselves, the x's, right? So I just want you to understand that each little interval here represents a quadrant, okay? So we're looking for the answer in quadrant 3. That's what we're looking for, okay? I'm saying that because these functions, you know, they intersect in two places. They intersect here in quadrant 1 between 0 and pi over 2, and they intersect in quadrant 3. I don't care for the solution in quadrant 1. I only care about the solution in quadrant 3. Do you understand this? So that's why I'm saying this.
So it'd be like 225 radians.
So that's it. Let's do it. Let's do it. So how do we find the point of intersection? What do we need to do? Set them equal to each other. So we need to set f equals to g of x. And we need to solve. So a sine equals to cosine. This is supposed to be in silent mode. Sure. Someone left a package in my front door. Okay. So sine equals cosine, and now we need to solve this. This is a little trigonometric equation, okay? And remember, we are really just interested in the answer from quadrant 3, but let's solve it between 0 and 2 pi. I don't really want to know all the solutions. I just want to know the solution between 0 and 2 pi. How do we do this? Well, there are many ways that you can try this, but for example, an easy way to do this is to divide both sides by cosine. First, realize that cosine cannot be 0 on this equation, because when cosine is 0, that happens right here, the sine is equal to 1, right? A pi over 2. When cosine is 0, sine is 1 or negative 1. This is the other case. The point is that when cosine is equal to 0, the sine will never be equal to 0, okay? So we can assume that in this equation, we can assume that cosine of x is different than 0. The reason why I'm saying that is because I'm going to divide by it, okay? I'm going to divide both sides by cosine. And, you always need to make sure that whatever you're dividing by is not 0. Otherwise, you have an issue. Why is this helpful? Because now sine over cosine becomes tangent. And then we get tangent of x equals to 1. And this is something easy to solve. So you just need to remember, what angle do you know whose tangent equals 1? Do you remember this? Remember, I told you there are special angles that you need to know: sine, cosine, tangent, all the functions. There is one of them whose tangent is 1. Which one is it? Pi over 4, 45 degrees. Okay? Tangent of pi over 4 is 1. So it turns out that here x equals, okay, so let me back up a little bit. We're solving this equation, right? So tangent is positive, so that means that we're going to get an answer. X is an angle for which tangent is positive. There are two possibilities for this, right? Where is tangent positive? In what quadrant is tangent positive?
1 and 3.
Quadrant 1, quadrant 3, right? So we're expecting an answer from quadrant 1, and we are expecting an answer coming from quadrant 3. And that's because this is positive. Yes? What's the answer in quadrant 1? The answer in quadrant 1 is pi over 4. What's the answer in quadrant 3? Be pi over 4 plus pi, right? Good. Pi plus pi over 4. You need to use the reduction formula. Do you remember this?
5 pi over 4.
Technically, you just proved
But
it.
what if it was not this and was something else? Like
Well, yeah,
if we
well,
had a 2
that's
in here or
another
something.
story. We're talking about this one.
Okay. So this one is pi plus pi over 4, right? Because the answer in quadrant 1 is always your reference angle, okay? So here's what's going on. So we have our pi over 4 over here. And then the other angle that have the same tangent as pi over 4 is this one down here. Okay? You do plus pi. And then just remember, tangent is sine over cosine. Here sine and cosine are both positive, and here sine and cosine are both negative. So the negatives cancel each other. Okay? And it keeps the same angle, which is pi over 4. That's the reference angle. All right, so it's pi plus pi over 4. So we get 5 pi over 4. Okay? And typically you would say plus 2k pi and plus 2k pi, like all the coterminals. But there's no need to do that because I don't care about stuff bigger than 2 pi or less than 0. Now, we are not really looking for quadrant 1. We are really looking for the solution in quadrant 3. So this is the one that we are interested in. So this guy here is 5 pi over 4. And if you want, you can say this one is also pi over 4. But we don't need that one, right? We only need the 5 pi over 4. Questions on how we solve this equation? Okay, so now we are ready. So the area that we're looking for, we're going to split it into two areas. Okay, area 1, area 2. So it will be area 1 plus area 2. And again, if you are 100% sure that they are symmetric, then you can do what your classmate said. If you know that the shape is the same, you just are in different positions, you can calculate 1 multiplied by 2. But be careful. Make sure that you are sure that's the case. Okay, so how do we calculate the first area? Is the integral from where to where? It would be pi over 2 to 5 pi over 4. And then who goes on top? F is on top and G is in the bottom, right? So that would be F minus G. I'm just going to write the function. So sine minus cosine dx. Actually, let me do everything in red because now the other integral is blue. And then plus, now the other integral is from where to where? So from 5 pi over 4 to 2 pi. And now this time, who is on top? Function g, which is cosine. That'll be cosine minus sine. Are we okay with this? All right, so now let's compute. All right, so integral sine. So that will be negative cosine. Integral of cosine, sine. So we get negative cosine minus sine. And then we need to evaluate this from pi over 2 to 5 pi over 4. Plus, then the other one, this would be sine plus cosine, right? Because it's minus cosine. And then this gets evaluated from 5 pi over 4 to 2 pi. All right, so let's do that. So let me see something here. But this guy is going to come in negative that we combine. Okay, so it's going to be negative cosine of 5 pi over 4 minus sine of 5 pi over 4. Then minus, I'm going to plug in pi over 2. Negative cosine of pi over 2 minus sine of pi over 2. That's the first parenthesis. Then we have plus. I'm going to do the second parenthesis. I'm going to write in everything, but you know, eventually you will realize there's some stuff here that are 0, and then you don't need to really worry about them. But let's just do it. So I plug in 2 pi, then minus, I plug in 5 pi over 4. Okay, so let's get the zeros out of the way. So let's see, in the second parenthesis, cosine of pi over 2, that's 0. So that one is gone. And in the third parenthesis, sine of 2 pi, that's 0. So that's gone. Now notice that in the first parenthesis, this guy is going to combine with this one. They are exactly the same number and they are both negative. Yes? So cosine of 5 pi over 4, what's cosine of 5 pi over 4? We're in quadrant 3. Cosine in quadrant 3 is negative, so that's going to be negative square root of 2 over 2. Yes? Because it's the same thing as pi over 4, but make it negative. So square root of 2 over 2, negative square root of 2 over 2, but with the minus becomes positive. And I need to multiply it by 2. So I'm going to have 2 times square root of 2 over 2. Do you understand this? Mm-hmm. Why times 2? Because this term comes up twice. But it cancels, the minus is gone. And then, let's see, we can play a similar game with this guy. This one, right? They're both negative also. So whatever they are equal to, multiply by 2. So sine of 5 pi over 4, again, in quadrant 3 is negative, and it's the same thing as cosine. Because pi over 4 is this special angle because it's also a triangle. Sine and cosine are the same. Okay? So it will be also negative square root of 2 over 2, but then times 2, and the minus make it positive. Okay? So plus 2 times square root of 2 over 2. And then in this parenthesis, we have a negative 1. Sine pi over 2 is 1, negative, but with the minus in front becomes plus 1. And then cosine of 2 pi is also equal to 1. Okay? All right. So these guys are gone. So we're going to get 2 plus 2 square root of 2. Because square root of 2 plus square root of 2 plus 2 square root of 2, and then 1 plus 1 is 2. All right. Questions? Are we okay with this? All right. So let's see. Let me give you one more, and then I want you to try it, and then I'm going to take attendance. Okay? Let's see. And then that would be the region R.
Wait, why is the two, square root of 2 positive and not negative?
Okay, so 5 pi over 4 is in quadrant 3, right?
Uh-huh.
Both sine and cosine are negative in quadrant 3.
Oh, so that cancels out the
But
negative.
then you have the negative,
Yeah,
so
yeah.
minus becomes
Right.
positive, right? And you understand the times 2,
Yeah.
because we have the same thing twice.
Yeah.
Are we good? So remember, and always be on the lookout to make sure that we get something positive as an answer. You get something negative, we did something peachy somewhere. Okay? Something is wrong somewhere. All right, so how about this one? So the region bounded by square root of x, the line 3/2 minus x over 2, and the x-axis. Okay? All right, so try this. Let me, how do we do this? What's the first thing that we should do?
Is there a way to do this without graphing? Like inputting the numbers and stuff?
Well, you have to do it algebraically, but in my opinion, it's more complicated. I mean, this is easy. Square root and a line.
Yeah, to an extent, right? Because this is easier, but then it gets harder to graph.
You're not gonna get crazy functions to graph. You're gonna get functions that, like I said, the basic functions. There is a list of 8 to 9 functions that you learn in pre-calculus. You see the formula, you need to know the graph back and forth. Those are what you're gonna get. And some polynomials. You know how to graph polynomials, like cubics and so on. You need to find the zeros, right? Remember what you did in pre-calculus. And even then, to actually be able to find where they cross, the points of intersection, all of that business, you need to solve an equation. That means finding the zeros. You're gonna find the zeros, might as well graph it. Because the hard part in graphing the function is knowing the zeros. Once you know the zeros, then, and you need to know the shape. And also when you do volumes, if you don't sketch the region, it's gonna be very hard for you to figure out what formula you need to use and how to use the formula. So you need to sketch the region. All right, so let's just figure out where these functions are gonna cross or not, okay? So that's what I'm gonna do before I even graph, okay? So I'm gonna set f of x equals to g of x, and let's determine if they're gonna cross. So this is 3/2 minus the square root of x equals 3/2 minus x over 2. Yes, they cross because this is square root and this is a line that comes down. They're actually gonna cross at one point. It seems. Okay, let me multiply everything by 2. Then square both sides. I mean, we can guess a solution. Can you guess a solution? Look, here I'm not really testing you on whether you can solve the equation or not. I'm testing you on finding the area. Can you tell me what solution?
Oh, yeah, 0.
No, 0 is not a solution.
Oh.
1,
Sorry.
right? 1. And you know that there is only one solution because if you draw the picture, this is a square root function, and then the line, it goes through 3/2. Let's say this is 1. Let's put 3/2 over here. The slope is negative 1/2, so the line goes down like this, right? So we are only gonna have one solution, and we can see it right here. Without having to actually solve the full equation, you can see that x equals 1 makes the two statements true, and we move on with our life. Do you understand what I'm saying? So if you realize that, just move on. You get your point, and then you work. Okay? I'm gonna solve it, but keep that in mind, because now we need to solve a quadratic. Okay? Which in general, that's what you need to do. But if you can spot the solution right away, why not? All right, anyways, let me just do it. So 4x equals 9 minus 6x plus x squared. Move everything to the right. So that's x squared minus 10x plus 9. Locally is something that we can factor. That's x minus 9, and then x minus 1. So we get x equal 9 or x equal 1. So here is the 1 that we wanted. And now 9 is extraneous. If you plug in 9 into the original equation, what do we get on the left-hand side? We get positive 3. On the right-hand side, we get 3/2 minus 9/2. That's negative 6/2. That's negative 3, right? So that's not a solution. So this one is strenuous. By the way, that x equals 9 would have been, remember that the square root is really a parabola cut in half, right? If you think about the other part of the parabola, which would be this one, you know, that line will cross the parabola down here again, right? That will happen at 9. That's the solution that we found. But that's not what we are concerning with. So we know now for sure that this happens when x is 1. And when x is 1, y is 1. Just plug into a square root function. So this is f of x equals square root, and let's say up here, that's a 3/2. And this is g of x equals 3/2 minus x/2. And let's find the x-intercept. So who can tell me what's this point for the function g? That's equal to 3. Remember, that's the x-intercept. You find it by setting the function equal to 0, right? This is 0 when x is 3. It's 3/2 minus 3/2. Yes? So this is a 3 right here. And we are interested in this area. The area bounded by the function f, the function g, and the x-axis. So this is what we're talking about. Yes? All right. How do we do this?
If this were, you would make it in regards to y.
It will be easier if we make it in regards to y. Good. You can do it in regards to x, but the problem is that you see from 0 to 1, the behavior from 0 to 1 is different than the behavior from 1 to 3. You see, from 0 to 1, there is no blue function, we only have the red. Yes, so you integrate the red function, but then from 1 to 3, you will have to integrate the blue function, and there is no red function. You understand this? So if you want to do it with respect of x, you will have to do it with two integrals. From 0 to 1, the function f, plus from 1 to 3, the function g. And no need to do top minus bottom, because the bottom here is always the x-axis. You understand this? But instead, let's go ahead and let's do it with respect of y, because that way, if I place my rectangle horizontally, if I place my rectangle like this, it's always the case that the right curve is given by the blue function and the left curve is given by the red function, right? And then we just imagine this rectangle moving from bottom to top. Along the y-axis, you are covering, you're sweeping through the entire region. Remember, what we're really doing is adding the for those rectangles. Okay? So I'm going to integrate with respect of y. Now there is something that is required if you want to integrate with respect of y. Let me change this. If you want to integrate with respect of y, so to integrate with respect of x, you need to have y as a function of x, like we're given in the problem. But if you want to integrate with respect of y, it's the other way around. You need to have x in terms of y. Okay? You also have to play with that idea, because sometimes it's not that easy to solve for the variable. Okay? Here it is. If y is equal to square root of x, how else can we describe this curve? That means x equals y squared, right? And then here, we have y equals 3/2 minus x/2. Just solve for x to write it in terms of y. Okay? So this would be x equals 2. So multiply by 2, so it will be 2y, so 3 minus 2y, right? Move the x over here and then the y. So 3 minus 2y. Did you understand this? Just multiply by 2, right? So you have 2y equals 3 minus x. Switch x on to y. Bring the x positive to 2y. Just do it, and you will see. It's pretty simple. Just do it. All right, so you have to do that, okay? So you need to solve for x if you want to integrate with respect of y. Again, nothing wrong with integrating with respect of x, but then be prepared to write two integrals. That's all. But in this example, I'm going to do this one with respect of y. So the area will be the integral. Let's see, from where to where? Look at the region. You have to focus on the y-axis. Look at the y-axis. From where to where? From 0 to 1. The top is y equals 1, right? And the bottom is y equals 0. So that will be the integral from 0 to 1. And always remember, here we need to put a right curve then minus the left curve, right? Instead of top minus bottom, now you need to do right minus left because you need to calculate the length of the rectangle. And then you do dy. Okay, so what's the equation for the right curve according to the picture? So I should change my colors. Right, so it would be the line. So 3 minus 2y. And then the left curve is, what's the left curve? Y squared. Remember, now you have to write everything in terms of y. Okay. Do you understand this? So now let's integrate. So let me just fix it. So this is the integral from 0 to 1 of 3 minus 2y minus y squared. And we calculate. So that's 3y. I mean, you solve this the same way that, imagine that y is x. It doesn't matter. Okay, at this point, it doesn't matter, the variable. So 3y minus, you can write 2 times y squared over 2, but as you know, the antiderivative of 2y is y squared, right? Just write y squared. Then minus y cubed over 3. And from 0 to 1, so that's 3 minus 1 minus 1/3. And then the rest is 0, right? So that would be 2 minus 1 over 3. And 2 is the same thing as multiplied by 3, 6 over 3. So 6 minus 1 is 5. So we get 5 over 3. Questions? And let's see, we have a couple of minutes left. So I'm going to go ahead. I'm going to actually calculate the same thing, but now let's do it with respect of x. So you see, we have to get the same number, but we need to compute 2 integrals, okay? Do you have a question before I move on? Okay, all right. And so note, we can do it with respect to x, but we need 2 integrals.
Wait, so what are you doing?
What am I writing? Read it.
No.
Instead of doing it with respect to y, we're doing it
Eh?
with respect to x.
Are you gonna do it again in respect to?
Yeah.
Oh, okay.
Just for you to see that, regardless of what you decide to do, you're gonna get the same answer, right? You have to get the same answer, and at the end of the day, you decide what you want. Now, there's one question in the homework that specifically asks you which one is better with respect to x or with respect to y. What they mean is, if you need more, if you need 2 integrals and with the other one you only have 1 integral, you should go with the 1 integral case. Like here, we will say it's better with respect to y. Okay, even though you may consider better with respect to x. That's really a matter of taste. But when you're doing that problem, by better here we mean solving the problem with 1 integral rather than using 2 integrals. You understand this? So when you're doing that question, the homework question, keep that in mind. All right, so if I want to do it with respect of x, that means I will have to place my rectangle vertically, and naturally the integral has to be split in 2, right? From 0 to 1, and then from 1 to 3. Is this clear to everybody? Because from 0 to 1, the red is the one that's on top, but then from 1 to 3, the red is gone, and now the blue is the one that's on top. Yes? That's why we need 2 integrals. So in this case, we're going to have the integral from 0 to 1 of the red function, which is square root of x, then plus the integral from 1 to 3 of the blue function, which is 3/2 minus x over 2. dx. Okay? All right, let's calculate. So this becomes, as you know, square root of x is x to the 1/2. So it's going to be x to the 1/2 plus 1 over 1/2 plus 1 from 0 to 1. And then the other one, so that's 3/2 x minus 1/2 x squared over 2 from 1 to 3. And then let's compute. So this one is x to the 3/2. So this piece right here, remember, is x to the 3/2 over 3/2, but that's really 2 over 3 x to the 3 half, okay? So as I'm gonna be working with that expression. So I plug in 1, I get 2/3 minus 0. That's what we get from the red part. And plus, now from the blue part, we plug in 3, so that's gonna be, let's see, that's gonna be 3 half times 3 minus 1/4 times 9. Then minus, I plug in 1, that's 3 half minus 1/4. All right, simplifying this, what do we get? That's 2 over 3 plus, so we have 9 half minus 3 half. That's gonna be 6 over 2, which is 3, right? That's a 3. I took care of this with this. And then negative 9 over 4 plus 1 over 4, because minus minus plus, that becomes negative 8 over 4, which is negative 2. And so we have 2 over 3 plus 1, and 2 over 3 plus 1. And this is 3 over 3, so that's 5 over 3. And of course, the same thing, right? Again, the point is that we use one integral by integrating, by doing it with respect of y, and then here we use two integrals with respect of x. The problem is that sometimes, even if you realize that with respect of y, you can get away with one integral, sometimes you cannot do this. Sometimes you cannot just solve for x the way we did it. Here it was easy to solve for x, but sometimes you have a function that's actually, you cannot solve for x, okay? And what do? Well, you have to integrate with whatever you can solve for, okay? So, but whenever possible, you know, just choose whatever is easier. Don't make it more complicated. But whichever you choose, you will get the same answer if you do it correctly, of course. All right, questions in calculating area?
This last thing we can apply to the other examples.
The other examples was better with respect of x. If you look at the pictures, for example, let's say here you want to integrate this one with respect of y, you will need to solve for x, you will have to be integrating inverse sine and inverse cosine. At this point, we actually don't know how to do that. We need to do integration by parts to know how to do that. Because really, when you solve for x, what you're doing is applying the inverse function. Because in the case below was easy. The inverse of the square root is the square function. That's easy. And the line is another line. But when the functions are more complicated like this, then it's probably not the best bet. Here, you could do either or. You can try it. But for example, here you will need to do, but that's not a big deal. Fourth root, but the fourth root is easy to integrate as well. It's just y to the 1 over 4, and then that one you could do it like that. But there is no point. I mean, we can also do it like this. So. This one, as I explained originally, if you put it horizontally to do with respect of y, you actually have to break into 3 integrals. Because you have this triangle, then a rectangle here in which neither blue nor red is part of the left or right, and then you have when the red begins, which is another triangle. So you will have 3 regions to calculate. So it's easier to do in one shot like this. So when you have the problem, you have the picture, you need to decide how to want a rectangle, vertical or horizontal. If you place it vertical, it's with respect of x. If you place it horizontal, it's with respect of y. And typically, you want to place a rectangle in such a way that the top is always the same and the bottom is always the same. The function doesn't change, okay? Or if it's horizontal, the right is always the same and the left is always the same, as much as possible. That's the idea. And this mindset is going to help you when we talk about volumes next time. Because there will be a rectangle that you need to place, and then we're going to be rotating regions to create some solids. But we're going to analyze it from the region point of view. No need to draw the solid. Okay? All right, guys. So